In order to use all these concepts in a nice framework, we used Snorkel. It's basically a package that came out of the Hazy Research Lab at Stanford. And so it's the nice thing about it is it's like has a nice friendly interface. It has Jupyter notebooks, and it's something you can get up and running very fast. And it puts all these all the things that I talked about in the earlier slide in a platform where you can easily start using it, right? So I'll go into some detail about what this pipeline looks like. The first part of the pipeline is where you have a subject matter expert telling you, okay, if this is the task, these are some things that I look for in the document. Maybe your subject matter expert is someone from biology or someone from linguistics, and they have basically a lot of domain knowledge, and what they're trying to do is trying to put their expertise into some kind of rules. And then we build these labeling functions using those rules. The ultimate goal is to use these labeling functions, apply them on your input data. So for our spouse example, we have, let's say, 3 labeling functions, lambda1, lambda2, and lambda3. Lambda1 says, does the word wife occur between the names? Lambda2 is this a name in the dictionary, and so on. So parallelly, we have our input documents, and we send it through a document parsing pipeline. In the case of Snorkel, it's spacey. So what it does, it separates the document into sentences. Maybe you want to extract some specific phrases or n-grams. You also have part of speech tagging for each of the words, and so on. At this stage, what you want to do is apply these labeling functions to all these parsed documents and get a label matrix. So the label matrix is basically a matrix of input data and labels, right? We can think of this as sort of a voting system. So you have your input data number 1, data point 1, and then what is the vote given by lambda 1, lambda 2, and lambda 3. Let's say lambda 1 says, yes, we're talking about a spouse names here. And lambda 2 says yes. Maybe lambda 3 says no, and so on. So now you have a matrix with all the input data and all the voting from all of these labeling functions. So the next stage is to understand, so all these labeling functions came from subject domain experts, and we understand that maybe these are not very strong indicators of labels for your training data. So what you want to understand is what is the accuracy of each of these labeling functions. The simple way we can think of it is a voting system and a majority vote, right? Let's say we had 20 labeling functions and 17 of them voted yes for data point 1 and 3 of them voted no. We automatically want to say, okay, maybe we don't believe in those 3 labeling functions as much as we do in the other 17 labeling functions. So this gives us an idea of accuracy of each of the labeling functions. If you understand a little bit more of the probabilistic graphical modeling scenario, we can also model this as a factor graph and say, okay, we have all these factor nodes between those variable nodes, and maybe there's some kind of relationship between these labeling functions. So one thing to be cautious about here is, what if all those 17 labeling functions were correlated in some way, or maybe they're just copies of each other? Then it's not valid to say that we believe in them more than those other 3 labeling functions. And this is what we take care of by doing this factor graph modeling. Basically, we say, maybe there are dependencies between these labeling functions. Let's code them using a node between those 2 labeling functions and learn them by using the data. Maybe you have this already from before because your subject matter expert told you, but it's also possible to learn it from your data. And this is one of the papers from the Hazy lab, and it talks about learning the structure of this dependency graph. So we have already graduated from the point where we had no label training data to a point where we have probabilistic training labels for each of our data points. And we can go ahead and build our the usual supervised learning models at this point. So this could be a logistic regression or a neural network, your LSTM, any kind of supervised model depending on the scale of or the volume of your input data, right? Okay, so what the supervised model really helps in doing is increasing the coverage. Maybe your labeling functions were not covering a lot of data that you had, and in that case, the supervised model, once it learns what you have from your noisy labels, you can apply it to more of your data. So that's the weak supervision pipeline using Snorkel. Let me talk about a little bit of work that we did at Chegg using this to develop labels for physics. So I used open source data in the form of glossaries, summaries, etc. And then I used popular terms from other subjects as a negative sample for training my weak supervision model. It had a lot of complexity just because this is academic data. So in the spouse example, when I say, okay, these two names are married or not married, there are not many other possibilities. They're married or they're not married. But here, things like a concept like electric field and charge and capacitance, they're really, there's a lot of interrelation between them and the concepts are intertwined. To understand the concept of capacitance, you need to understand the concept of an electric field and charge. So let's say, for example, my goal in doing this labeling is so that I can route the question to the correct expert. It's not necessary that an expert on electric field and charge is also an expert on capacitance. Because if you look at, the course path, capacitance is something that you learn after you've learned about charge. So maybe this is something to keep in mind when you're building models using weak supervision. So for this particular use case, so then it makes more sense to use some hierarchical rules on top of whatever we already have with the keywords and whatever the subject matter expert said to build the right kind of model. So there was a lot of iteration in this process because at Chegg we work closely with the product. So we want to always know what is next in line to be launched, how is this going to be used, how is my model going to be used, especially when you are interacting with students and showing whatever we are building to the students. So we had some iterations with product and understood what the use case was and then went back and modified my labeling functions or added some more labeling functions so that we can get the right kind of output. Conclusions. Rule-based approaches are great for exploring unknown data, and we were able to label 70% of some of the unknown pool of data that we had just by using weak supervision. And Snorkel's great because it provides a way to quickly iterate and modify just the labeling functions. And the research group is also very active, and they are constantly working on improving what functions are available to use. And the other lesson that we got from this was communication with product clearly and frequently as possible is helpful. Yep, that's all I have. And thank you. Yes.
So in terms of learning curve, how easy or hard was it to start working with Snorkel?
For me, it was, I could use it the same day that I started installing it, but could be because I have a technical background, but I have seen the Snorkel folks work with a lot of biologists, especially with things like, oh, can you label this tumor as malign or benign or malignant, or can you look at, they're also working with images now. So I think for them, maybe it's a little bit longer,